Hello everyone, I'm Chirag Gulati, a BTech computer science student at Amity University, Punjab, currently virtually interning at Altair. Today, I'm excited to walk you through a project I've been working on, which is based on predicting alcohol consumption using machine learning. So before we dive in, I want to thank Altair for providing me access to RapidMiner, which is a fantastic tool for data science, as you will also get to see during this video. The primary aim of our project is to build a classification model predicting whether an individual is a regular drinker or a non drinker. Now, let's start with the dataset that we have. This is the dataset that we have. This is the smoking and drinking dataset that I found on Kaggle. So, over here we have more than 990,000 examples, which is a pretty large data set, with 24 regular attributes, which is 24 columns, one of which is our target column, which is the final categorical column that tells us whether the person is a drinker or not. All right, so now that we have our data set loaded into RapidMiner, our next step is going to be data preprocessing. In the data preprocessing sub-process, what I've done here is four main tasks. First is I remapped hearing. All right. The second is going to be remapping the smoking column. And then I generated a new column, which is BMI. BMI is a very good factor for comparing people's health because it is relative to their weight and height. So this is the column that I added, and I also added a site total, which is the arithmetic sum of the site left and site right columns. Till now, what we see here is we don't have a BMI column, and the site and the hair left and right have a value of either 1 or 2. So after I run the data preprocessing one, we get a BMI column. The hair left and right have a value of 0 and 1 now, and we have a site total column, and we also have a change in the smoking column where instead of values 1 to 3 we now have keywords like never, still, and used to but quit. All right, so as we're done with the data pre-processing aspect of the project, our next step is going to be to move on onto the EDA, or the exploratory data analysis, which is something that I've already done and I'll walk you guys through with the help of my documentation. So the first thing we noticed was that the number of Y and N labels in our target column were approximately the same. This equilibrium is very important as it enables us to train a model that is not biased towards any specific label. The next interesting fact that we could see in our EDA was when we plotted out sex versus drinking habit plot. Over here, we saw that in the Y label, in the people that drink, uh, it was hugely populated by males, whereas conversely, in the no labels, females dominated. So, this gender specific distribution provides insight into the drinking habits of the genders. We also see a similar trend with the smoking habit. Over here, we can see that the never label in the smoking habit is hugely dominated by females, whereas in the still and used to but quit categories, females can be seen in a very less number compared to the number of males. Another interesting graph that I found out was the drinking versus smoking habit one. Over here, we can see that the majority of people who don't drink also never smoked. This shows a very high relation between the two factors. Now, this is quite interesting. All right, so now that we're done with the exploratory data analysis, the next step in our project is going to be dummy encoding, because this is how we need to deal with columns like sex and the smoking habit column, because they have text values which cannot be understood by the machine learning model. So in order to train the model, we need to convert it into binary form, which the machine can very easily then understand. So when we run it, we convert the columns, like this is the sex column now, which is ones and zeros, and then we also have the smoking ones, which have also been converted to ones and zeros. So now after the dummy encoding, we set the role of our target variable as a label. Over here, we have one special attribute, which is our final target variable, the column that we're trying to predict. After setting the role, what we do is, see, right now we have a lot of values. BMI has a different range, height has a different range, age has a different range, weight has a different range. So the model that we train might think that the number 170, that the height is more useful to predict if a person drinks or not rather than the BMI or the weight. whereas we know that this is not true. So we need to give all of these, we need to keep all of these columns within the same range, or you can say we need to normalize them. There's different ways of normalizing the data. The way that I'm using, the method that I'm using here is range transformation. So when I run this, yeah, so we can see over here that all of our values now, all of our numerical values are going to be within the range of 0 to 1. So now, after the normalization, our data is ready to be split into two parts. One of 70% of the data, which is going to be the training set, and then 30% of the data, which is going to be the testing set. All right, so let's split the data. Okay, so now what we're going to do is we're going to send in the 70% of the data, which is the training set, into our optimized models, the optimized models grid block. So over here, we're going to apply a lot of models. We're going to apply decision tree, naive bayes, random forests, logistic regression, random tree, decision stump, gradient boosted trees, deep learning, and XGBoost. We're going to calculate the performance of different parameters, and then the best one is going to be sent to the apply model operator, and with the rest of the 30% of the data, which is unseen to the model as of now. After that, this is going to go into the performance operator and give us the final result of each of the machine learning models turn by turn, whichever one we are applying over here. So let's try out with XGBoost right now. Okay, so this is the final answer that we see. We get an accuracy of 73.79%. This is our truth table. This is for XGBoost, the one that we just ran. And this is the highest accuracy we could get out of any other models. I'm just going to show you the rest of the models in the documentation itself, because it's going to take us a lot of time to run every one of these again. So naive Bayes gave us an accuracy of 69.62%. Logistic regression gave us an accuracy of 72.73%. And we can see the rest of them right here. Okay. So as we can very clearly see, the highest accuracy we get is 73.79%, which is from XGBoost.